Hi everyone, what's up? Today I'm going to show you how you can parametrize a cycloid. So a cycloid is pretty much the curve that will describe a point. So let's say we have this point here. If you just simply spin this wheel on a horizontal surface without slipping, meaning it's just rolling, what is the curve described by the position of this point, okay? That is what a cycloid is, and that is what I'm gonna parametrize today, okay? I pretty much just wanna find what is the position vector of this point here, okay? With respect to theta, you could parametrize this curve with respect to different parameters. You could use time, for instance, but in this case, I want to use theta, okay? I think it's the simplest case. So yeah, let's do it. So if we want to find what parametric curves describe, what parametric functions describe the curve taken by this point, well, really we're just asking what is the position vector of this. So what is this position vector? We could call it, I'm just gonna call it big R, okay? What is big R? What is it equal to? That is gonna be the position vector that we need. Now, we're gonna use a very common principle in math, which is if you wanna find something, instead of finding that thing directly, you can find things that are equal to that thing, okay? So instead of finding R, we will find things that allow us to say that they are equal to R. So we're gonna find things that are equal to R, but not R itself. And then we're gonna be able to get to R. It may sound kind of weird, but I just wanna show you what I mean by that. So to find R, we can write R in terms of different vectors, okay? Now, what is one vector we could use? Well, what path could we take using vectors to get to this point? Well, notice that you could travel this horizontal distance, then you could travel this vertical distance up, and then you can travel the radius of the circle to wherever the point is, okay? Now, something you could also do is maybe you could try to find the height of the point with respect to this x position in here, but then that would be slightly hard because that position would not be very easy. I mean, with respect to this theta, this is not going to be easy to parametrize, okay? It's not going to be easy to find what vector describes that height, okay? So the easiest thing to do here is to just simply find this path or find the vectors that describe this displacement, then displacement up to the center of the circle, and then traveling the radius, okay? I want to find vectors describing these displacements. So I will say the following. Let's say we're going to have an origin. I'm going to do that. No, we'll use black, actually. So let's say this is going to be O. And let's say I'm going to call this point, I'm just going to call it A. And let's call this one, it's going to be center, so let's call it C. That's going to be point C. And then this point here, I'm just going to call it P, okay? So you have O, A, C, and P. So we're going to go from O to A, then from A to C, and then from C to P. And if we add up all those vectors, we're going to get to R, okay? So let's write that equation. So we're going to have that R is going to be equal to O to A, so OA plus AC plus CP, okay? Now, this is what I said at the beginning, which I probably didn't phrase it in the best way possible. But what I wanted to say is that we're not going to find R directly. We're going to find things that are equal to R. These three vectors, or really the addition of these three vectors, will give us R. So we're going to find, instead of finding R, we're going to find these three vectors and then we're going to add them up, okay? So now let's ask the question, what is OA? Well, notice that OA is always going to be the distance, the horizontal distance, traveled by the center, okay? So now that distance, this is a very interesting principle. If you've taken physics, maybe you can grasp this idea. So the circumference traveled by this portion, so now I'm going to use black for this. This circumference in here, so this portion over here, this circumference will be equal to this area over here, okay? Not this area, sorry, this region of space over here, okay? So this horizontal distance will be equal to the circumference, this arc length, traveled by the angle, you could maybe call it the angle, or the CP vector with respect to C, okay, using C as an origin. So this arc length will be equal to the horizontal distance. Now, we know the horizontal distance will be equal to the the x component of OA. Now, what is that horizontal displacement equal to with respect to theta? Well, I'm gonna say the following. So we know that, of course, we need to do this in radians. So we know that 2 pi r, oh, well, should I? No, I'm actually just gonna tell you, there's a formula. If you're doing calculus, there's this, well, this is not really calculus, but this is something you would do probably in multivariable calculus. So if you're doing calculus or if you're parametrizing equations and curves, you probably know that the arc length, if you're using radians, the arc length, given some theta and some radius, is going to be equal to r theta. So this portion over here is just going to be L is equal to r times theta, where r is equal to the radius of the circle. So I'm going to write this here, r, just for notation. Yeah, so we know this horizontal distance is going to be r theta, which is really nice because r is going to be a constant and theta is going to be our input, so we can let it vary. So yeah, I'm just going to say this will be equal to OA. So we know it's going to have a horizontal component, and we know that horizontal component is going to be r theta, okay? So whatever distance we've traveled, whatever horizontal distance we've traveled, that's going to be the magnitude and the x component of OA, okay? And this will be 0, okay? Now we have OA. Now what about AC? Well, let's do AC. Now AC is going to be really easy because it's really just going to be a constant vector. It's not going to change its direction as you change theta, and its magnitude is not going to change because this wheel is not getting any bigger. So this vector AC is really just going to be 0 in the x component and r in the y component, okay? Probably should have written label my axis. I apologize. This should be x and this should be y. So this is going to be, AC is going to be OR, okay? Those are going to be the components. And now, the only vector that we have left is going to be CP. Now, CP is slightly trickier. Something you may notice about CP is that you're just really in a circle. And if you're in a circle, you can maybe treat this as a triangle using the Pythagorean theorem. So let me show you this. Yeah, I'm going to do the following. So I'm going to need a horizontal axis and a vertical axis. And let's say the following vector. So let's say this vector, and this is going to be theta. Let's say this is going to be our vector CP, okay? So it's going to be C and this will be P, okay? So now I'm just kind of like grabbing a section of this diagram. So now if this is the scenario that we have, and we know CP is going to give us a circle, well, we know that if you have a circle, this is pretty much a right triangle. If you draw its components, you can think of it as a right triangle. You have this vertical component and you have your horizontal components. And of course, you're going to have right angles here. So now, the only thing that we need to ask is, well, what is the horizontal and vertical components of CP in this diagram? Now we know these are right angles, which is really nice because then that means that given this theta, well, we know this vertical component is going to be equal to, so we know that first in theory, yeah, well, now I wouldn't say in theory because in practice and in theory and in everything, if you're going to find the vertical component, given this theta, you need the magnitude of CP. That is very good. Again, this wheel is not changing, so the magnitude of CP will be equal to R, okay? So then we can just use, a couple of trigonometric identities here to find this magnitude. So I'm going to do the following. I'm going to say that sine theta is going to be equal to, so we know it's going to be the opposite over the hypotenuse. Now this opposite is going to be the horizontal component, okay? Is that going to be the, yeah, that should be the horizontal component, or yeah, that's going to be, we're using x as a horizontal, so yeah, it's going to be the x component, so I'm going to call this CPx, the horizontal component, divided by r, okay? And this is supposed to be an r. And now what about, well, if we say cosine theta, well, what's that going to be equal to? Well, then we know that's going to be the vertical component, so we know it's going to be this section over here. And now we know the vertical component is going to be CP sub y divided by r, okay? That r looks so bad. Yeah, that's better, okay? That's an r. So we have CPy divided by r. and then we just simply need to use these values. We just simply need to plug these values into a vector notation or a vector form for CP, okay? So from this, we're gonna have that. I will do it over here, okay? So we're gonna say that CP is gonna have the following components. So the x component of CP with respect to theta, we know it's just gonna be r times, and now we gotta be careful here. Notice that since we're starting, we're rotating in a clockwise direction, so we're doing like this. This is gonna have a negative component, okay? So this is gonna have a negative component. That's the right way to describe it. So this is really gonna be minus r sine theta, okay? Notice we're on the bottom left quadrant, so it's gotta be negative and also negative down, negative left, negative down. So this will be, CP will be minus r sine theta, that's gonna be our x component. And then our y component, we know is gonna be r minus r cosine theta, okay? So this is what we get. And now the only thing that we need to do is we just simply need to add up all of these components to get r, okay? So we know r is going to be OA plus AC plus CP. So we're going to have r. Then, so now let's see. If we add up all the x components, so we have r theta 0 plus minus r sine theta. We know that's going to give us r theta minus, r theta minus, we got an r here, r sine theta. And now the y components, we're going to have OA, it's got a component of 0, then r plus, in this case it's going to be r minus r cosine theta, okay? And this is the parametric function, the parametric curve that you get for a cycloid, okay? The parametric expression for a cycloid. Our parameter is going to be theta, the angle, or the angle given by p with respect to the angle given by p with respect to the vertical axis. And yeah, these are going to be final equations that you get. You could factor out here an r, and maybe you could get a better form because you have r everywhere. So you could just say that this will be r times theta minus sine theta, comma 1 minus cosine theta, okay? So if you have a unit circle, a unit wheel, then this would be just this portion. Those would be the equations. But for any r, you just, you're scaling. This makes a lot of sense, really. If you have a greater r, pretty much your position is just your vector, you're just gonna be farther away from the origin. This is one way in which you could interpret what this is saying, because r is gonna be a factor that's gonna allow us to scale up or down this vector over here, okay? These parametric functions. So yeah, that's been the entire video. Hopefully you enjoyed it. This is how you can parametrize a cycloid. It's really nice. It's really easy, I think, as long as you can think about, instead of finding r, just really try to find things that are equal to r, which are just these three vectors. That's a nice approach. So yeah, that's been the entire video. Hopefully you enjoyed it, and see you in the following one. Bye.